Welcome to another episode of Return Notes. Today we'll be talking about financial quantitative analysis. More specifically, we'll be talking about modern portfolio theory. Modern portfolio theory is the idea that you can maximize return in an investment portfolio while minimizing risk, and we'll be using Markowitz portfolio optimization in order to accomplish this. If you've ever wondered how hedge fund managers or other fund managers decide how much to invest in any particular asset, they use modern portfolio theory to construct their portfolios, and in today's video I'll be teaching you what that is and how you can implement it using Python. We will be covering a wide array of topics today, including diversification, financial risk, risk modeling, and how to implement these ideas in Python. So let's dive right into our Jupyter notebook and start coding. The first thing we're going to do is import the libraries that we'll be using in this video. So we'll import NumPy and use the alias NP. We'll import pandas with the alias PD. We'll also import scipy.optimize, which is what we'll be using to actually do the optimization of our portfolio. We'll import that as SCL. And then we're going to import matplotlib pyplot is PLT. The next thing we need to do is set up our parameters. The first parameter that we need to determine is the number of assets that we have, and we'll set that equal to 4. And we will simulate returns for these assets over a certain number of days, which we'll set to 1000. Once we have that, we can get the ticker symbols for each of our assets, which we'll just say stock A, stock B, stock C, and stock D. In order to actually simulate the returns for these assets, we will use this randn function, which simulates random values that follow a normal distribution. We will simulate one return for each day, so these will be daily returns, and then we're going to simulate this for each of our 4 assets. This function will return values that have a mean of 0 and a standard deviation of 1. In the stock market, on a typical day, you might see a fluctuation of about 2%. So we're going to multiply this by 0.02, which will keep our mean as 0, but our standard deviation will be about 2%, which is more in line with what we might expect to see in the actual stock market. And then we'll convert this into a data frame. And we'll pass in our returns, and our column names will be the ticker symbols. And then we can take a peek into our returns data frame. The next thing we need to do is we need to get the mean and covariance of our total portfolio. So we'll create this variable mean returns, and we'll use our returns data frame and just get the mean. And then we want to annualize that, so we will multiply this by 252. We're using 252 instead of 365 here. That's because there's about 252 trading days in a year. You can't trade on holidays or weekends. And we also want to get the covariance, which is how these assets move together. So once again, we'll use our returns data frame, and we'll get the covariance and then annualize it. Make sure you use an asterisk here. Now we're going to define a few functions. So the first function we want to define will give us the portfolio performance. We will pass in some weights, which is the percent that we will allocate to each of our investments. We'll pass in the average returns for our stocks, and a covariance matrix, which details how various stocks move together. Our portfolio return will simply be the weighted average of the weights and the returns for each stock. The portfolio standard deviation will be slightly more involved to calculate. Remember, standard deviation is the square root of variance. So we'll use the square root function, and then we'll have our variance in between these brackets. To calculate the variance, we'll use the weighted average. We'll pass in our weights and transpose them. And then we'll have our covariance matrix with our weights. And make sure you close that out with 3 parentheses. And then we'll return the tuple that contains our portfolio return and our portfolio standard deviation. The next function we want to define will be a minimum variance function. So we'll define our function here. Once again, we'll pass in weight, our mean returns, and our covariance matrix. And here we're going to return the portfolio performance of a portfolio that has these weights, these mean returns, in our covariance matrix, and we want to get the standard deviation, so we'll access that second element of the tuple, which we will use using that first index. Next, we need to set the constraints and bounds of our optimization. So we'll start with our constraints. What this constraint will do is ensure that the sum of all of our weights equals 1, meaning we can allocate 100% of our available resources. And to do this, we first need to give it a type, and we'll set that equal to EQ, because this is an equality constraint. We need the total sum of all of our allocations to equal 1. And then we're going to pass in a function, and this function will be a lambda, and this lambda will ensure that the sum of all of our weights equals 1. So we'll create this temporary variable x, and then we'll pass in the sum of x minus 1. We're subtracting 1 because this will actually add to 0. So if we do our sum minus 1 and that equals 0, then that means our sum matches 1, and this will satisfy our constraint and perform the way we want it to. So then we can go ahead and close this out, and then we can set our bounds. Our bounds will be a tuple, and then we're going to pass in bounds of 0 to 1 for each of our assets. Make sure you spell tuple correctly here. Now we've arrived at the point where we can actually get our optimal portfolio. This next function is very large, so I'm not going to type it all out on camera. I'm just going to paste it, and then we can talk about what each section of code is actually doing here. We're defining this function that optimizes our portfolio, and we're passing in the mean returns and covariance of our assets that we can invest in. We get the number of assets that we have, and we're just going to start by weighting them equally. The thing we're going to minimize is this minimum variance function, which is what we define up here, which just returns the standard deviation, and that standard deviation is what we want to first minimize, and we're going to minimize that assuming we have equal weights. This args function is what takes the arguments for this function, and so that's actually what's doing this up here, these functions that we define with these parameters. We need to give it a method. We're going to be using the sequential least squares quadratic programming, which is a common optimization method, and then we give it the bounds and constraints that we defined up here. And then we're going to get the weights and the return and standard deviation for our portfolio. The next thing we want to minimize will be our negative Sharpe ratio. Sharpe ratio is just the ratio of return to risk, and we want that to be higher. And since we can only minimize here, we're going to make this negative and then minimize that. So then we're going to pass in our Sharpe ratio function, and we're going to minimize that. And then we're going to store all of the results in this data frame here that we are going to return. In order to actually use this function, we are going to create this optimal portfolios variable, and we are going to call our optimized portfolio function. We're going to pass in the mean returns and our covariance matrix. And then we can print our optimal portfolios. Make sure you spell optimized portfolio correctly here. The last thing we're going to do is simulate 10,000 different portfolios, and we're going to visualize the results. So we're going to loop through each of these portfolios, get the return, standard deviation, and Sharpe ratio, and then we're just going to create a plot that shows where is our efficient frontier and where is our optimal portfolio. So you can see we have our minimum variance portfolio here and our maximum Sharpe ratio portfolio here. Remember that Sharpe ratio is a ratio of return to risk, so that's really the portfolio you want to be targeting here. That's it for today's video. Make sure you like, comment, and subscribe so you don't miss an upload. If you're interested in quantitative analysis or financial analytics, make sure you subscribe and click the notification bell. I have videos on my channel about using Monte Carlo simulations in Python for retirement planning, or finding the best stock in Python using actual stock market data from Kaggle. So make sure you like, comment, and subscribe, and let me know if you like these more financial based videos, and just let me know what you think. Thanks for watching, and I will see you in the next video. One last thing, if you're interested in data analytics, I have a ton of web scraping content on my channel. If you're interested in scraping Instagram or Twitter or any website, I have all of those videos on my channel, so make sure you check those out. And once again, just make sure you like, comment, and subscribe. And now I'll really see you in the next video.